And next up, it's Beth Nowadnick, and she is talking about coupled structural distortions, domains, and control of phase competition in polar samarium barium manganese oxide.
All right, thank you for the introduction. So my focus today is going to be on understanding and controlling the crystal structure of this polar rare earth manganite. So this work that I'll be talking about recently appeared in this PRB paper, and I'd like to acknowledge my collaborators on this work, Jinggang He, who's currently at Northwestern, and Craig Feeney at Cornell University. So the rare earth manganites have been studied extensively in the context of the colossal magnetoresistance effect. Today I'm going to be focusing on an A-site ordered variant where due to the large size mismatch of the rare earth and barium cations, they can be synthesized in this layered form. This is what the electronic and magnetic phase diagram looks like as you vary the rare earth ionic radius. You go from a charge and orbitally ordered CE type antiferromagnetic insulating phase. I'm showing this over here where it involves these ferromagnetic spin zigzags. And then as you increase the rare earth ionic radius, you go to A-type antiferromagnet or ferromagnetic metals. So right now I'm going to focus in specifically on this samarium barium manganese oxide compound, which in addition to being a charge and orbitally ordered CE antiferromagnetic insulator, also was shown in a number of experiments a few years ago, has a polar crystal structure which enables additional functionality. You can also think about interesting couplings between the polarization and these other degrees of freedom. So there's been a lot of study of the rare earth manganites, especially their electronic and magnetic degrees of freedom, but there's been less work on their crystal structures, which are also very complex. So this structural aspect will be what I'll focus on today. So the outline for the rest of the talk is I'm going to first look at the ground state crystal structure and show you how some nonlinear couplings between the structural distortions are key for actually stabilizing this structure. Then I'll look at the domains and the domain walls, and then at the end I'll look at how we can use this understanding to think about stabilizing some of the competing electronic and magnetic phases in this compound. So before I get to that, one slide on our theoretical approach. So I'll be combining group theoretic analysis with DFT plus U calculations as implemented in VASP. For all the calculations here, I've set U to 4 and J to 1.2 EV. I selected these values so that the computed ground state reproduces the experimentally reported magnetic and crystal structures as you go across the phase diagram varying the rare earth ion. All right, so the ground state structure of samarium barium manganite, it crystallizes in this polar P21AM phase. And we can decompose this distorted structure into a high symmetry reference structure with the symmetry P4/MMM and 4 symmetry distinct structural distortions. So these symmetries here are labeled by these irreducible representations of P4/MMM. So these distortions are an out of phase octahedral rotation distortion, a breathing distortion which couples to the manganese 3+ manganese 4+ charge order in this compound, a low symmetry distortion that transforms like sigma 2 that encompasses displacements of the atoms in a stripe-like pattern, and then finally a polar distortion. So we can assess the contributions of these different distortions to the ground state by looking at their the amplitudes from decomposing the structure. We can do this both for an experimentally reported structure and also a structure relaxed with DFT. And the key thing is we find that most of the distortion amplitude comes from the octahedral rotation and from this low symmetry stripe distortion. So we can learn some more about this ground state structure by next looking at energy surfaces. So what this is we start with a high symmetry structure over here on the left and then freeze in each of these 4 structural distortions in separate calculations. One here is the amplitude of the distortion that occurs in the DFT relaxed ground state. And what we find is kind of interesting because we see that the octahedral rotation distortion lowers the energy, but the breathing and polar modes both increase the energy as they're frozen and they're stable. And in addition, this stripe distortion very slightly decreases energy and then also becomes stable. So this seems kind of curious because all 4 distortions occur in the ground state, yet only one of them seems to be really unstable here. So what's going on? So we can understand this by looking at coupling terms in the free energy between these structural distortions. So here I'm showing some third-order coupling terms in the Landau expansion of the free energy. First, there is a coupling between the breathing distortion and this stripe distortion. So here in the stripe distortion, you can have different amplitudes of displacements on 2 different sublattices indicated by these black and white arrows. That's the meaning of this S1 and S2. There's also a coupling between the octahedral rotation and the stripe distortion. And then finally, there's a trilinear coupling between the rotation, the breathing mode, and the polar mode. So we can look at the effect of these couplings on the energetics by then going back to our energy surface and starting here where we have one of the distortion amplitudes fixed, we can then freeze in a second one, and that resulting energy surface will show us the impact of that coupling term on the energy. So for example, here, this blue one, we've fixed the octahedral rotation, we're freezing in the stripe distortion. You can see it's lowering the energy. Up here, this black highlighted one, we've fixed the stripe distortion, freeze in the breathing distortion. We see there's a strong lowering of energy. And finally, we can keep going with this, and over here on this final panel, we perform calculations where 2 distortions are fixed and we freeze in the final one. This brings us to the ground state energy. And so the key thing is we can notice that these coupling terms between the distortions play a very important role in stabilizing the ground state. I'm not showing the polar distortion on this plot, but performing similar energy surface calculations with the polar distortion, we find that it is induced via these coupling terms by a hybrid improper-like mechanism. So a reason to be interested in these coupling terms also is these distortions coupled to the electronic and magnetic degrees of freedom, so these can give us some sort of interesting insights into those states as well. So for example, we've found that the breathing mode couples to this, which couples to the electronic charge order, occurs together with this large amplitude set of stripe displacements. And so this is, while we still need to understand kind of some of the microscopic mechanisms of this, this is quite a different picture of the charge order state than is often discussed in the literature of charge orders, which is the models typically focus just on electronic degrees of freedom and electronic instabilities. And interestingly, there's some recent work from Lena Krukutis's group at Cornell. They did some electron microscopy on a different manganite, but they saw in the charge order phase actually a set of stripe displacements. All right, so now let's zoom out a little bit and look at the domain structure, and these couplings that I've talked about in the first part of the talk will be key for determining that structure as well. So I'll particularly be focusing mainly on the structural domains here, although there's also electronic and magnetic domains in this system. So first of all, for the structural domains, there's orthorhombic twins. And these, we can label them by different orientations of the stripe order parameter. So this order parameter is actually a 4-dimensional quantity. In orthorhombic twin 1, the first 2 components here are non-zero. So we were only dealing with 2 components in the first part of the talk because we were just talking about one twin domain. And then in orthorhombic twin 2, the second 2 components are 0. So over here on the left, we have the stripes are going vertically. Over here on the right, they're going horizontally. Now, if we focus in on one orthorhombic twin domain, we can look at what are the structural domains that actually occur within that twin domain. So now we just need to deal with this two-dimensional part, S1 and S2, the stripe displacements on the two sublattices. So we can draw this order parameter, represent the order parameter in this two-dimensional space, and represent the domain as a point in this space. So just the labeled by the A and B, the amplitudes of the displacements on the two sublattices. So this is one domain. So in fact, there's 8 structural domains here, corresponding to different orientational variants. And then by using the coupling term, once we've chosen for a given domain the direction of the stripe order parameter, the coupling terms will determine what is going on with the other order parameters there. So for example, this coupling between the octahedral rotation and the stripe distortion tells us that the domains in each quadrant have the same sense of the octahedral rotation. This coupling between the breathing mode and the stripe distortion tells us that the domains in these light pink and blue quadrants have opposite phases of the breathing and charge ordering. And then finally, this trilinear coupling tells us that the domains in the hatched and solid regions have opposite polarization. So this plot sort of efficiently summarizes this set of coupled structural domains here. So now let's look at the domain walls. So within this order parameter space approach, a domain wall is represented as a path between the two domains. So here's an example of one here. And so I'm going to get some insight into these domain walls, I'm going to look at sort of what's equivalent to an intrinsic ferroelectric switching path. So I'll look at, how does the structure of the energy surface evolve as we go from here to here. So, with this approach, we won't get, quantitative aspects of domain walls, but it can give us some insight into the relative energetics of different types of domain walls. So in particular, in going from this domain here to this domain, we can look at what is the midpoint or barrier structure that you need to go through. It's indicated here by this green dot, and it has this symmetry PBAM. And then with density functional theory, I can constrain to that symmetry and relax the samarium, barium, manganite structure and see what its energy would be in this barrier structure, and we get out these particular energies where 0 is the ground state energy. Here I've done these calculations with ferromagnetic and A-type antiferromagnetic spin orders. The CE-type order is not stable in this structure. We can also look at other types of, and so this wall here corresponds to a charge order and a polar domain wall. We can also look at other walls, for example, going from between these two domains, construct the barrier structure and calculate its energy. We find this one's much higher, and then there's this other third one here going through this purple point, which has sort of a barrier in between. And we could construct past these other domains, but the barriers would be the same as what I already have up here. However, we do need to consider a path from this domain, one of these domains, to a domain in the orthorhombic twin. And we can look at the barrier for that path, and that actually has a very low energy barrier. All right, so an interesting, so we have this set of paths, and then a question is, are these the lowest energy paths between these domains, or could we find something lower? And in particular for these two paths here that have that high barrier, we can construct a lower energy two-step path. So what I mean by that is, for example, for this path, instead of going directly from one domain to the other, we could instead go to the domain in the orthorhombic twin through this low energy barrier and then go back via this two-step path. And so what that means is that this high energy path here is unstable to splitting into these two lower energy paths. So to summarize that, we find that there's these two low energy paths between domains. This one here, which corresponds to a charge order 180 degree polar wall, the one here, which is a ferroelastic and 90 degree polar wall, and all the other paths between domains are unstable to splitting into pairs of these low energy paths. Now, sort of an interesting consequence of having this large number of domains in this set of paths or domain walls with an energy hierarchy is you can get a formation of domain wall vortices where you have multiple domain walls merging together. And by analyzing this, we find two types of these domain wall vortices where we have either 3 domain walls merging or 4 domain walls merging involving these low energy paths. All right, so I'll just finish up by talking a little bit about stabilizing competing phases in samarium, barium, manganite. So the first is looking at the domain walls. So all of the barrier structures that I identified in the previous analysis, they all host either ferromagnetic or A-type antiferromagnetic metallic states. So could these competing states stabilize at the domain walls of samarium, barium, manganite? And in particular, the structural and the CE-type antiferromagnetic domains are coupled. So the CE-type ground state magnetic order is actually interrupted at these structural domain walls, which could give some room for these competing magnetic phases to stabilize. So based on these bulk energy surface calculations, I can't make a definitive statement about whether these states would happen or not. But there is some interesting examples from other manganites. For example, an enhanced conductivity observed at charge order domain walls in a Ruddleston Popper manganite and some ferromagnetic metallic edge states in manganite strips. The second way to look at stabilizing competing phases is then going to thin films and looking at epitaxial strain. And so by looking at the strain dependence of these different phases, we've found that under compressive strain, this ferromagnetic metallic phase can be stabilized. All right, so that brings me to the end of my talk. I'd just like to briefly end with a couple points sort of related to outlook. So one is, I've focused this talk just on this particular manganite, samarium, barium manganese oxide, but many of our results generalized to other half-doped manganites, both A-site ordered and some non-A-site ordered ones. So exploring this in the context of other rare earth manganites. And then we'd also be very interested in collaboration with the experimental group to explore this domain structure further. So thank you for your attention.
So open the floor to questions. One over here.
Thank you for your talk, very nice. Have you calculated the polarization? Maybe you mentioned that, the ferroelectric polarization. Did you
the ferroelectric polarization? I have not calculated it myself, but from the experimental literature, they were estimating it was like a couple microcoulombs per centimeter squared.
Sorry, how much?
A couple microcoulombs per centimeter squared.
Thanks.
It's not a structural question, but have you quantified the charge order? I mean, how the charges of manganese, nominally manganese 3+ and manganese 4+?
Yeah, so within the DFT calculation, it's not 3+ and 4+, but there's certainly a variation in this checkerboard. So it's maybe differing by like 0.4 or so, something like that.
Anyone else? So I know this is all about samarium, but on one of the first slides you showed the plot of all of the different rare earths, and neodymium was right on a phase boundary.
Yeah.
Do you think the same analysis would apply to neodymium, and maybe that's a better place for trying to stabilize different competing phases?
Yes, I think. I think that could be a good place to look, because then the phases might be closer in energy. I know that sort of the experimental literature on this neodymium, barium, I think there's sort of been some different structures and magnetic orders reported as the ground state. But there is one paper I've seen that actually reported a polar structure for that one as well.
Okay, if there's no more questions, we'll go on to, one more.
Just a quick comment. I mean, this material looks terribly similar to lead zirconite. in many aspects, but you have the chemical stacking, but actually the nominal order parameters are the same, actually.
Yeah.
Of course, here you also have a polar distortion, which I guess you wouldn't have if you didn't have the baryon, samarion stacking. And it really looks very much like lead zirconate. So I don't know if you are familiar with the literature on the compound, but I think it would be nice to have a look because...
Yeah, I know you have a
some-
paper on lead zirconate, and it does have this stripe distortion or sigma 2 mode. So yeah, so it's
the
very
stripe distortion
similar.
is exactly what people call the antiferroelectric motion in lead zirconate. And it's dominated by the tilts, as in your case. It's
Yeah,
very
yeah,
similar.
no, I agree. That's good for further comparison, I think, yeah.
Okay, thank the speaker.